16.16 hours. That's how long it takes 3i Atlas to complete one cycle. Brighten, dim, brighten, dim. Perfectly regular. And for months we told ourselves it was just rotation. An irregular comet tumbling through space. Except someone did the math. And the math doesn't work. A nucleus that's small cannot produce brightness changes that large. Not through reflected light. Not even close. Which means something else is glowing. Something surrounding the nucleus. A cloud. A shell. Expanding and contracting like a lung. And if it's breathing, then it's not rotating. It's pulsing. Deliberately. On a schedule. Stay until the end, because this 16-hour rhythm has reignited the one theory astronomy tried desperately to bury. And now scientists are quietly using a different word. Mothership. If you're as captivated by this mystery as I am, go ahead and like this video and subscribe so you catch every development as this story continues to unfold. Leave a comment telling me where you're watching from, what time it is in your corner of the world, and whether you think we're being told everything about what's really happening out there. Part 1. The moment the math broke the narrative. Picture this. It's early 2023, and astronomers are tracking something strange. A visitor from beyond our solar system, catalogued as Comet 3i Atlas, is putting on a light show. Every 16.16 hours, like clockwork, it brightens and dims, brightens and dims. The official explanation? Simple. It's an irregularly shaped comet nucleus, tumbling through space, reflecting sunlight as it rotates. Different facets catch the light at different angles. We've seen this before, case closed. Except the math doesn't work anymore, and when I say it doesn't work, I mean it collapses spectacularly. The officially accepted size estimates for this nucleus range from about 440 meters to 5.6 kilometers in diameter. That's our best measurement from Hubble, from Webb, from ground-based observatories, so we know roughly how big the solid core is. Now here's where things get uncomfortable. Take that nucleus, even at the upper end of the size range, and calculate how much sunlight it can reflect. Go ahead, do the geometry. Factor in the albedo, the cross-sectional area, the distance from the sun. The numbers are straightforward. The problem is this. The brightness fluctuations we observe are massive. We're talking about 20 to 30% amplitude swings in luminosity over each cycle. That's not subtle. That's not a gentle flicker. That's the object getting dramatically brighter, then dramatically dimmer, then brighter again on a rigid schedule. And when you run the calculations for how much light a small rotating nucleus can reflect, you hit a wall. A nucleus of this size simply cannot produce brightness changes of that magnitude through reflected sunlight alone. It's physically impossible. The cross-section is too small. Even if one side were perfectly reflective ice and the other side were pitch black tar, the difference wouldn't be enough. Not even close. We're off by orders of magnitude. So if the nucleus isn't causing the brightness changes, what is? The answer has been staring at us the whole time, wrapped around the nucleus like a shroud. The coma. That fuzzy cloud of gas and dust that surrounds every active comet. We've always known it was there, glowing faintly in the sunlight, scattering photons. But we treated it as background noise, a static halo. The nucleus was the star of the show. Except now we have to accept something radical. The coma isn't static. The coma is what's changing. The coma is dominating the light output. And the coma is doing something very, very strange. This is what researchers are now calling coma luminosity dominance. The cloud around the nucleus is responsible for the observed brightness variations, not the solid body itself. And if that's true, then we're not watching a rotating rock. We're watching something else entirely. Something that periodically pumps out gas and dust in enormous quantities, creating a glowing shell that expands, brightens, then fades away, only to repeat the cycle exactly 16.16 hours later. This isn't rotation. This is breathing. Enter Avi Loeb, the Harvard astrophysicist who's never been afraid to say the quiet part out loud. Loeb looks at this 16-hour rhythm and sees something familiar. Not from nature, from engineering. He calls it a heartbeat, a periodic energy expenditure, a duty cycle, and he proposes something that makes most of his colleagues deeply uncomfortable. What if this isn't a comet at all? What if we're watching a propulsion system? What if those brightness pulses are mass ejections, timed and controlled, designed to alter trajectory or maintain course? What if this object is mechanical? Now, before you dismiss this as science fiction, consider what we've just established. The standard model, the one that says this is just a weird comet with an irregular shape, has mathematically failed. It cannot explain the observations. We are officially in uncharted territory. The rotating rock hypothesis is dead. So what replaces it? A natural explanation would require extraordinary internal dynamics, pressure chambers, volatile reserves, structural coherence across repeated outbursts, all synchronized to a clock. Or, and this is where it gets uncomfortable, we accept that the simplest explanation for a periodic, high-amplitude, precisely timed energy release might not be natural at all. It might be intentional. This is not a gentle adjustment to the comet model. This is a collapse, and once you see it, you can't unsee it. The object we thought was a dirty snowball might actually be something far stranger. Something that breathes, something that pulses, something that, if Loeb is right, might be watching us just as closely as we're watching it. And here's the thing that keeps astronomers up at night. If the coma is breathing, then it has to expand. Gas doesn't just glow in place. It moves, it spreads. And when you calculate how far that gas can travel in 16.16 hours, the numbers become terrifying. Part 2, the 25,600 kilometer shell. Why breathing? Beats spinning. Let's talk about scale, because this is where the hypothesis stops being abstract and becomes visceral. If 3I Atlas is periodically ejecting gas, that gas doesn't hover politely near the nucleus. It explodes outward at high velocity. The proponents of the mechanical model, the ones who think we might be looking at an engine, suggest an escape velocity of around 440 meters per second. That's fast. Not relativistic, but fast enough to matter. Now take that velocity and multiply it by the duration of one cycle, 16.16 hours. Do the math, and you get an expanding shell roughly 25,600 kilometers thick. 25,600 kilometers. Let that sink in. That's nearly twice the diameter of Earth. Every cycle, this object is creating a glowing cloud almost as wide as two Earths stacked together. And then it fades, and then it does it again. Perfectly, predictably, over and over. Here's how it works, step by step. Outgassing begins. Maybe it's triggered by solar heating, maybe by an internal mechanism, but gas and dust start pouring out of the nucleus. They expand outward in all directions, or perhaps in a directed jet, depending on geometry. As the cloud expands, it scatters sunlight. The coma brightens. We see this as the upswing in the light curve. But gas doesn't stay dense forever. As it spreads, it thins. The particles drift farther apart. The optical thickness drops. The coma dims, becomes transparent, fades into the background of space. And just as it disappears, the next cycle begins. Gas pours out again. The shell rebuilds, the brightness spikes. Rinse and repeat. Think of it like a lung. Inhale. The coma fills, expands, glows. Exhale. The coma dissipates, fades, vanishes. Inhale, exhale. On a 16-hour rhythm. That's the breathing metaphor, and it's disturbingly apt. But here's what makes this so strange. Comets don't breathe. Comets are chaotic. Jets fire randomly as pockets of volatile ice get exposed to sunlight. Tails grow and twist depending on solar wind and radiation pressure. Brightness fluctuates erratically because sublimation is messy, uneven, driven by surface cracks and thermal gradients. You might get periodic behavior if the nucleus rotates and a single jet sweeps across your line of sight, but even then, the timing drifts, the amplitude varies, the pattern degrades. 3I Atlas doesn't do any of that. The light curve is clean, the period is stable, the amplitude is consistent across multiple cycles. This is not chaos. This is coherence. And coherence, in nature, is rare. It requires either an improbable alignment of conditions or a mechanism that enforces regularity. A feedback loop. A resonance. Or, and this is the option that makes people nervous, a control system. So what kind of internal structure would a natural comet need to sustain this? You'd need a massive reservoir of volatiles, buried beneath the surface, insulated enough to avoid continuous sublimation, but accessible enough to vent periodically. You'd need structural integrity that survives repeated pressure buildups without fracturing the nucleus into pieces. You'd need some kind of thermal or mechanical cycle that resets every 16 hours, synchronized perfectly with the object's rotation or solar heating pattern. And you'd need all of this to work flawlessly, cycle after cycle, with no degradation, no drift, no chaos. It's possible, barely. But it requires stacking assumption on top of assumption, whereas the alternative, the one Loeb and others are whispering about, requires only one assumption: that this object was built, that the 16-hour cycle isn't accidental but intentional, that we're watching a machine doing exactly what it was designed to do: release gas, generate thrust, adjust trajectory, move on. And if you think a massive periodic gas release sounds implausible for natural processes, wait until you see where that gas is going. Because the geometry of the jets, the direction of the outflow, doesn't just complicate the story, it breaks it wide open. Part 3. Jet Geometry. How the anti-tail complicates everything. Late November 2023. An observatory in Thailand captures images of 3I Atlas, and something in those images doesn't make sense. There's a jet, a clear, well-defined stream of material ejecting from the nucleus, but it's pointing the wrong way. It's aimed toward the sun. Comets don't do that. Let me be very clear about this. Cometary tails and jets are blown away from the sun by radiation pressure and the solar wind. That's basic physics. Photons hit dust particles and push them outward. Charged particles in the solar wind drag ionized gas away from the nucleus. The result is always the same. Tails point away from the sun. Jets, when they're visible, tend to follow the same rule, or at least they're deflected in that general direction. A sunward jet, a jet actively streaming toward the sun, is not just unusual, it's wrong. Now this observation is controversial. Not everyone agrees on the interpretation of those images. Some argue it's an optical illusion, a projection effect, a trick of geometry. But if we take it at face value, if there really is material being ejected sunward, we have a serious problem. Because once gas and dust leave the nucleus and head toward the sun, they should be immediately blown back by radiation pressure. The sun is a fire hose of photons and particles. Anything moving toward it gets hammered. For a sunward jet to persist, to remain visible, the ejection velocity would have to be enormous, fighting against the solar wind. Or the ejection would have to be continuous, constantly replenishing the material that gets blown away. Or, and this is the option that makes the most sense if you're thinking about propulsion, the jet is being actively vectored, aimed, controlled. Let's explore what a natural explanation would require. You'd need a vent on the nucleus, positioned on the anti-sunward side, the dark side facing away from the sun. Solar heating from previous exposure would have warmed subsurface volatiles, building up pressure. When the vent opens, gas blasts out in the only direction it can, toward the sun, because that's where the pressure gradient points. Fine, that's plausible for a single event. But for this to happen repeatedly, across multiple cycles, you'd need the vent to remain in the exact same position relative to the sun every time it fires. And since the nucleus is presumably rotating, that means the rotation axis, the vent location, and the sun would all have to be aligned in a very specific, very unlikely configuration. And that alignment would have to hold without drift for weeks or months. The odds of that happening by chance are not good. And every time you stack up another coincidence, another improbable alignment, the natural explanation becomes less convincing. At some point, Occam's razor starts cutting the other way. Maybe the simplest explanation isn't that nature got incredibly lucky with vent placement and rotation. Maybe the simplest explanation is that the jet is pointed sunward because someone wanted it pointed sunward, because thrust in that direction slows the object down, decelerates it, adjusts its trajectory. This is where the propulsion hypothesis starts to feel less like wild speculation and more like the only model that fits all the data. A sunward jet makes perfect sense if you're trying to brake, if you're trying to change course, if you're approaching a target and need to fine-tune your arrival. And if that's true, if 3I Atlas is actively maneuvering, then the 16-hour cycle isn't a geological accident. It's a flight plan, a sequence of burns, timed and executed according to mission parameters, a duty cycle. And duty cycles, as anyone in aerospace engineering will tell you, are how you conserve fuel and extend mission duration. You don't fire your thrusters continuously. You pulse them. On, off, on, off. You manage your propellant. You balance thrust with efficiency. You operate on a schedule. And 16.16 hours, recurring with mechanical precision, starts to look a lot less like nature and a lot more like engineering. So the question becomes, If this is a duty cycle, what's the mission? Where is this object going, and why is the timing so precise? The answer might lie in the next part of the puzzle, the one that turns this from a curious anomaly into something genuinely unsettling. Because when you plot 3i Atlas's trajectory, when you project where it's headed, you find something waiting for it, something big. Part 4. Duty Cycle Logic. Lessons from Propulsion Engineering. Let's talk about how machines work, specifically how propulsion systems work when they're designed for long-duration missions. Because if you're trying to cross interstellar space, or even navigate within a solar system, you don't have unlimited fuel. You have to be smart, you have to be efficient. And one of the most effective strategies is to operate in pulses. On, off, on, off. This is called a duty cycle, and it's everywhere in engineering. Your car engine fires in bursts, satellite thrusters activate for a few seconds, then shut down to conserve propellant. Ion drives on deep space probes like Dawn or Hayabusa fire intermittently, nudging the spacecraft along over months or years. The advantage of a duty cycle is that it lets you accomplish the same net change in velocity using less power and less fuel. You build up thrust during the active phase, then coast during the inactive phase. The momentum carries you forward. You don't need continuous burn, you just need periodic kicks. And if you're an interstellar probe travelling for millions of years, this isn't just efficient, it's essential. Because no matter how advanced your civilization, you can't pack infinite fuel. You have to ration it. You have to plan. Now let's compare that to what we see with 3i Atlas, a 16.16-hour cycle. Regular as a metronome, each cycle produces a massive outflow of gas and dust, bright enough to dominate the light curve. Then it shuts off, the coma fades, the object coasts, and 16 hours later it happens again. That's a duty cycle. And if you're thinking about propulsion, if you're thinking about trajectory control, the pattern fits perfectly. Fire the engine, eject mass, generate thrust, wait, fire again. Contrast that with natural cometary behaviour. Sublimation-driven jets are messy. They depend on where the sun is relative to the nucleus, how deep the volatile ice is buried, whether there are cracks in the surface letting pressure escape. You might get some periodicity if a single jet rotates in and out of sunlight, but the timing will drift as the orbit changes, as solar heating varies, as the volatile reservoir depletes. You won't get the kind of rock-solid regularity we see with 3i Atlas, not across dozens of cycles, not without some kind of stabilizing mechanism. So let's explore two competing models. Model A is the natural explanation. Call it the cryovolcanic pressure cycle model. You've got a large reservoir of volatile ices beneath the surface. As the nucleus approaches the sun, or as it rotates into sunlight, heat penetrates the crust. Pressure builds. Eventually, the pressure exceeds the structural strength of the overlying material, and the crust fractures. Gas explodes out in a violent outburst. The pressure drops. The crust refreezes or reseals. The reservoir repressurizes, and the cycle repeats. That's plausible. We've seen similar behavior on bodies like Enceladus, where tidal heating drives periodic geysers through cracks in the ice. But Enceladus has a heat source. Tidal flexing from Saturn provides continuous energy input. 3i Atlas, on the other hand, is moving through interstellar space, far from any star most of its life, then briefly swinging through the inner solar system. The thermal environment is different, the energy budget is different, and most importantly, the regularity is different. Enceladus's geysers are steady, not pulsed on a 16-hour clock. For the natural model to work, you need the heat penetration depth, the volatile composition, the structural properties, and the rotational period to all align perfectly. And you need that alignment to persist without degradation. It's not impossible. But it requires a very specific, very fragile set of conditions. Model B is the artificial explanation. An internal power source, maybe a reactor, maybe stored chemical energy, drives a propulsion system. Periodically, the system activates, ejects mass, generates thrust. The ejected material forms the coma, which scatters sunlight and creates the brightness pulse. Then the system shuts down, conserves energy, waits for the next burn. The 16-hour interval is programmed, part of the mission profile. The amplitude is consistent because the fuel flow is controlled. The jet geometry, including that troublesome sunward component, is intentional, designed to adjust velocity or direction. Which model fits the data better? Model A requires stacking multiple unlikely conditions and hoping they all hold. Model B requires accepting that we're looking at technology. And I know which one makes people more uncomfortable. But discomfort isn't evidence. The question isn't what makes us comfortable. The question is what explains the observations. And right now, the artificial model is doing a better job. Because here's the thing, if this is a duty cycle, if this is propulsion, then the object isn't drifting aimlessly through space. It's going somewhere. It has a destination. And when you calculate where that destination might be, when you project the trajectory forward, you find something waiting. Something that shouldn't be there by chance. Something that looks a lot like a target. Part 5. The Jupiter question. A trajectory that shouldn't exist. 3I Atlas is not bound to the Sun. Its orbit is hyperbolic, which means it came from interstellar space and unless something changes it will leave again, is passing through. A tourist. Except tourists don't usually have such precise itineraries, and the itinerary for 3I Atlas includes a very specific date. March 16th, 2026. That's when the object is predicted to make its closest approach to Jupiter. Not just somewhere in Jupiter's neighbourhood, close to Jupiter's Hill sphere. Let me explain what that means. The Hill sphere is the region around a planet where its gravity dominates over the Sun's gravity. For Jupiter, that radius is enormous, about 53 million kilometres. If you're inside that sphere, Jupiter is the boss. Its gravitational influence controls your motion. And if you're trying to enter orbit around Jupiter, or release a probe into Jovian space, getting inside the Hill sphere is essential. It's where the fuel requirements drop, where you can execute maneuvers without fighting the Sun's pull. Now, here's the uncomfortable question. What are the odds that a random interstellar object, following a hyperbolic trajectory, just happens to pass close to Jupiter's Hill sphere? Not impossible. Space is big, Jupiter is big, trajectories cross all the time. But when you factor in the other anomalies, the regular outgassing, the sunward jet, the duty cycle pattern, the cumulative probability starts to collapse. It's like rolling a die and getting sixes over and over. Eventually you start wondering if the die is loaded. Some researchers, particularly those in Loeb's camp, argue that this isn't coincidence. They suggest that the non-gravitational accelerations, the tiny velocity changes caused by outgassing jets, are being used to steer, to fine-tune the trajectory, to aim for Jupiter. And if that's true, then the object's path isn't random. It's navigated, plotted, executed. Non-gravitational accelerations are real. We measure them all the time on comets. When gas jets fire, they push the nucleus slightly, altering its orbit. The effect is small, but over long timescales it adds up. Usually these accelerations are treated as noise, something to correct for when calculating orbits. But what if they're not noise? What if they're signal? What if every burn, every pulse is a course correction? If you're crossing interstellar space, even modest thrust can have huge effects, because you're travelling for millions of years. A tiny velocity change early in the journey becomes a massive positional change by the time you reach your destination. You don't need high thrust, you just need time. And 3I Atlas has had all the time in the universe, so if it's headed toward Jupiter, if that March 2026 encounter is intentional, it could have been planned millions of years ago, with periodic burns along the way to stay on course. And that raises the next question. Why Jupiter? What's so special about the largest planet in our solar system? If you're an interstellar probe, if you're designed to explore new star systems, Jupiter is the obvious first stop. It's gravitationally dominant. It has a massive magnetosphere, a complex system of moons, an intense radiation environment. It's scientifically interesting. And from a mission planning perspective, it's useful. You can use Jupiter's gravity to slingshot into the inner solar system, or to break and enter orbit, or to deploy secondary probes toward the moons or even toward Earth. Jupiter is a hub, a waypoint, a logical target. So here's the scenario. An interstellar object, potentially artificial, enters the solar system on a hyperbolic trajectory. It exhibits periodic outgassing consistent with a propulsion duty cycle. It appears to vector thrust, possibly to decelerate or adjust course. And it's heading for a close encounter with Jupiter's Hill sphere on a specific date. If you were designing a mission to explore a new solar system, this is exactly what you'd do. Of course, none of this is proof. We don't have direct evidence of navigation. We don't have telemetry. We don't have infrared signatures of a reactor. We don't have resolved images of a spacecraft. What we have is circumstantial. A pattern of anomalies that don't fit the natural model, but fit the artificial model uncomfortably well. And the more pieces you add, the harder it becomes to dismiss. Because here's the thing, this isn't the first time we've seen weird objects behaving strangely in our solar system. It's just the first time the math has failed, so completely that we can't ignore it. And when you look back at other visitors, other anomalies, you start to see a pattern. A pattern nobody wanted to see. A pattern that suggests we might not be as alone as we thought. And that pattern is where we're headed next. Part 6. When interstellar visitors behave wrong, the pattern nobody wanted to see. Let's rewind. October 2017. Astronomers detect an object moving through the inner solar system, and within days they realize it's not from around here. Its trajectory is hyperbolic. It came from interstellar space. They name it One-Eye Oumuamua, Hawaiian for scout or messenger, and the name turns out to be more appropriate than anyone expected. Because Oumuamua doesn't behave like a comet, it doesn't have a tail, it doesn't show obvious outgassing, but it accelerates anyway, deviating from a purely gravitational trajectory. The acceleration is small, but it's there, measurable, consistent. The scientific community scrambles for explanations. Maybe it's outgassing, but the gas is too faint to detect. Maybe it's shaped like a pancake or a cigar, and radiation pressure from sunlight is pushing it. Maybe it's a hydrogen iceberg sublimating invisibly. Every explanation requires stretching assumptions, stacking coincidences. And then Oumuamua leaves the solar system before we can get a good look, and the debate continues without resolution. 2 years later, August 2019, we detect 2I Borisov, another interstellar visitor. But this time, it behaves exactly like a comet. It has a tail. It outgasses visibly. Spectroscopy shows familiar chemistry, water and carbon monoxide and cyanogen, the usual cometary suspects. Borisov is boring, predictable, natural, and in a way that makes Oumuamua even stranger, because now we know what a normal interstellar comet looks like, and Oumuamua wasn't it. Fast forward to 2023, 3I Atlas arrives, and immediately the alarm bells start ringing again, because this isn't Borisov, this is something else. The light curve is bizarre, the periodicity is too precise, the coma dominance calculation doesn't work for a natural comet, the jet geometry is wrong, and once again, we're forced to ask the uncomfortable question, are we looking at two classes of interstellar visitors? The normal ones, like Borisov, that fit our expectations, and the anomalous ones, like Oumuamua and 3I Atlas, that don't? Here's a hypothesis that nobody wants to say out loud. Maybe the galaxy is full of natural interstellar objects, planetesimals ejected during star formation, comets kicked out by gravitational interactions, debris from collisions. Those are everywhere. Trillions of them drifting through the void. Most of them are dead, inert, frozen. Some of them, like Borisov, are still active, sublimating as they pass near stars. Those are the ones we expect. But maybe, just maybe, there's another category. Objects that aren't natural, objects that were sent, probes, scouts, and maybe those objects are rare, but not so rare that we'd never see one. Especially if they're designed to visit stars, to navigate, to be noticeable. The selection effects here are brutal. We can only detect interstellar objects when they pass close to the sun, when they're bright enough or fast enough or weird enough to stand out. That's a tiny biased sample. Most interstellar objects sail through the outer solar system undetected. So the ones we do see might not be representative. They might be the exceptions, the outliers. And if some of those outliers are artificial, if they're designed to be robust, to survive interstellar travel, to operate in hostile environments, they might actually be more detectable than natural objects, brighter, stranger, more active. Oumuamua accelerated. 3I Atlas pulses. Both objects exhibit behavior that strains natural explanations but fits artificial models disturbingly well. And if you accept that possibility, if you entertain the idea that we might have detected two technological probes in the span of 6 years, then the next question is obvious. How many more are out there? How many have we missed? How many are watching us right now, invisible in the dark? The alternative worldview, the skeptical one, says we're seeing natural diversity. Interstellar objects come from different stellar environments, different formation conditions, different chemical compositions, maybe objects from the outskirts of other solar systems, never heated by their parent stars, behave differently than our familiar comets. Maybe Oumuamua and 3I Atlas are just exotic variants, natural but strange, and we're projecting our own hopes and fears onto them. That's possible. It's even likely if you trust that nature is more inventive than we imagine. But it doesn't explain everything. It doesn't explain the regularity of 3I Atlas's light curve. It doesn't explain the sunward jet. It doesn't explain the Jupiter trajectory. And at some point, the skeptical explanation requires just as much special pleading as the artificial one. You're still stacking assumptions. You're still invoking coincidences. The only difference is that one explanation makes us feel comfortable, and the other makes us feel small. So maybe 3I Atlas is natural, an extreme outlier, a 1 in a billion comet with bizarre internal structure and impeccable timing. Or maybe it's something else, a member of a fleet, a probe, a messenger. And if that's true, then the story isn't about one object. It's about what that object represents, a presence, an intelligence, a civilization that reached across the stars and left breadcrumbs for anyone curious enough to look. But before we go too far down that road, let's consider the most sophisticated natural explanation still on the table. The one that tries to save the comet model by imagining something extraordinary beneath the surface. Something that might, just might, explain the breathing. The geyser patch hypothesis. And if it works, it could shut down the artificial model entirely. But if it doesn't, if it breaks under scrutiny, then we're out of natural options. And that's when things get truly strange. Part 7. The geyser patch. Hypothesis and its breaking point. Imagine a comet nucleus, a few hundred meters across, irregular in shape, pockmarked with craters and fractures. Most of its surface is inert, covered in a dark crust of refractory material, silicates, carbon compounds, stuff that's been baked by cosmic rays for millions of years. But beneath that crust, in one specific region, there's a pocket of volatile ice. Water, carbon dioxide, maybe methane, a reservoir sealed away, insulated from space by the overlying crust. And as the comet approaches the sun, as sunlight starts to warm the surface, heat begins to penetrate, slowly, millimeter by millimeter. The ice warms, pressure builds. Eventually the pressure exceeds the tensile strength of the crust. A crack opens, a vent, and suddenly, explosively, gas and dust blast out into space. The outburst is violent, ejecting material at hundreds of meters per second, creating a massive coma. But the venting relieves the pressure. The gas reservoir cools, refreezes, the vent seals, and then, as the nucleus rotates, as the heated region swings back into sunlight, the cycle begins again. Heat penetrates, pressure builds, the vent opens, gas explodes out. This is the geyser patch hypothesis, a single active region, driven by solar heating, producing periodic outbursts synchronized to the rotation period. On paper it works. It explains the periodicity. It explains the large coma. It even explains the brightness pulses, because each outburst would create a temporary surge in scattered light. And it doesn't require anything artificial, just volatile ice, solar heating and structural dynamics. Natural processes. Extreme, yes, but natural. But let's stress test this model. Let's see where it breaks. First, the volatile reservoir. To sustain dozens of massive outbursts, each creating a coma tens of thousands of kilometers wide, you need a lot of gas. Not a pocket, a lake, an ocean. We're talking about a substantial fraction of the nucleus's total mass being volatile ice. And it all has to be concentrated in one region. That's possible, but unusual. Most comets have volatiles distributed throughout their volume, not localized in a single patch. You'd need a very specific formation history, maybe a collision that buried a chunk of pure ice beneath the surface, or a compositional gradient left over from the object's birth. Second, structural integrity. Every time the geyser fires, it's fracturing the crust, ejecting material, weakening the structure. Over time, you'd expect the vent to widen, the crust to collapse, the reservoir to fragment. Yet 3I Atlas has been doing this for months, maybe years, without apparent degradation. The light curve stays consistent. The period doesn't drift. That requires remarkable structural strength, or some kind of self-sealing mechanism that repairs the vent after each cycle. Again, possible, but it's another assumption. Third, the rotational alignment. For the geyser patch to produce a regular 16.16-hour cycle, The nucleus has to rotate with that period, and the active patch has to be positioned such that it faces the sun at the right time in each cycle. If the spin axis is tilted or if the patch is offset, the solar heating cycle won't match the rotation period. You'd get beats, harmonics, irregular timing, but we don't see that. The light curve is clean, so the geometry has to be just right, another coincidence. And fourth, the jet geometry. Remember that sunward jet? If the geyser patch is on the anti-sunward side, then gas ejected from it would naturally stream toward the sun, which fits the observation. But as we discussed earlier, maintaining a sunward jet against radiation pressure is difficult. The ejection velocity would have to be very high, or the jet would have to be continuously replenished. And if the patch is on the anti-sunward side, it's not receiving direct sunlight. So how is it being heated? By thermal conduction through the nucleus? That's slow. Too slow to explain the rapid pressure buildup needed for explosive outbursts. You can patch these problems. You can add more assumptions. Maybe the nucleus has high thermal conductivity. Maybe the volatile reservoir is pressurized by internal heat, not solar heating. Maybe the structure is reinforced by some exotic material, but at this point we're building a Rube Goldberg machine. Every fix creates a new constraint. Every constraint requires another unlikely condition. And the natural model, which started as the safe conservative option, is now looking just as contrived as the artificial one. There's another piece of data that complicates things further. Spectroscopic observations of 3I Atlas show abundant water ice and large icy grains in the coma. That fits the geyser model, but they also show spectral slopes more consistent with D-type asteroids than trans-Neptunian objects. D-types are primitive, carbon-rich, thought to have formed in the outer solar system or even beyond. They're dark, they're old. And they're not typically associated with vigorous cometary activity. So either 3I Atlas is a D-type that happens to have a massive volatile reservoir, which is weird, or it's something else entirely. And then there's the carbon dioxide to water ratio. Recent observations suggest unusually high CO2 relative to H2O, higher than typical solar system comets. That could indicate formation in a colder environment, farther from the star, where CO2 ices are more stable, which supports the interstellar origin. But it also suggests the object's composition is unusual, possibly shaped, by processes we don't fully understand. Cosmic ray processing, radiation damage, chemical alteration during millions of years in the void. So the geyser patch model can be made to work, but only by stacking assumption upon assumption. And at some point, you have to ask whether you're explaining the data or explaining it away, whether the model is constrained by evidence or by our desire to avoid uncomfortable conclusions. Because here's the thing, if the natural model is this fragile, this dependent on unlikely coincidences, maybe we're asking the wrong question. Maybe the question isn't whether 3I Atlas can be natural. Maybe the question is whether it's more likely to be natural or artificial. And when you frame it that way, when you weigh the probabilities, the artificial model starts to look less like wild speculation and more like the hypothesis that fits. Not because we want it to be true, but because the alternatives have all failed. And if we're willing to entertain the artificial hypothesis, if we're willing to consider that 3I Atlas might be a probe, then the next logical question is this. If it's a probe, is it transmitting? Is it sending data? Is it talking? And that's where things get really speculative, really strange, and really, really interesting. Part 8 is 3I Atlas broadcasting, the coma as antenna theory. What if the periodic brightening isn't just propulsion? What if it's communication? What if the massive coma, that expanding shell of gas and dust, isn't just an exhaust plume but a signal amplifier? A scattering medium designed to modulate electromagnetic radiation, turning the entire object into a transmitter. This is the coma as antenna theory, and it's one of the wildest ideas in the 3I Atlas discourse. But it's not entirely without precedent. In astrophysics, we see natural masers, regions where gas molecules amplify microwave radiation through stimulated emission. Water masers, methanol masers, hydroxyl masers. They're bright, coherent, and detectable across interstellar distances. The gas acts like a laser, but for radio waves. Now imagine an artificial version. A probe that periodically ejects gas, ionizes it or excites it, and uses it to scatter or amplify a radio signal. The coma becomes an antenna, a dish, a scattering screen, and the 16-hour cycle becomes the transmission schedule. For this to work, you'd need several things. First, a controlled emission source, a transmitter located at or near the nucleus, generating radio waves or some other form of electromagnetic radiation. Second, a dense coma with the right optical properties to scatter or amplify the signal. Third, timing. The emission has to be synchronized with the coma expansion, so that the signal is modulated by the changing density and geometry of the gas cloud. And fourth, a spectral window. The signal has to be at a frequency that can propagate through space, that isn't absorbed by the interstellar medium or drowned out by cosmic noise. Now here's where things get into fringe territory. There have been claims, mostly on social media and in less reputable outlets, that 3i Atlas transmitted a Fibonacci-patterned pulse at 1420 MHz. 1420 MHz is significant because it's the hydrogen line, a natural frequency associated with the most abundant element in the universe. SETI researchers often monitor this frequency, because any sufficiently advanced civilization would know we'd be listening there. It's a universal calling card, but let's be very clear. There is no peer-reviewed, independently verified evidence that 3i Atlas has transmitted anything. No observatory has published data showing a coherent signal. No radio telescope has detected structured pulses. The claims are unsubstantiated. They could be misinterpretations, hoaxes, or wishful thinking. Until we have reproducible data from multiple sources, the signal hypothesis is pure speculation. That said, speculation is fun, and it's instructive. Because even if 3i Atlas isn't broadcasting, the fact that people are seriously considering it, that researchers are thinking about how such a signal might work, tells us something important. It tells us that the object's behavior is strange enough, anomalous enough, that the artificial hypothesis is no longer absurd, it's on the table, and once it's on the table, all the downstream implications become fair game. So let's speculate. If 3i Atlas were broadcasting, what would be the motive? Reconnaissance. Sending data back to its origin, reporting on the solar system's structure, composition, activity. Maybe it's transmitting images, spectra, measurements. Or maybe it's self-advertising, a beacon, a marker, announcing its presence to anyone capable of listening, signaling that it's here, that it's artificial, that its creators exist. Or maybe it's communicating with other probes, a network of interstellar scouts, coordinating, sharing information, building a map of the galaxy. Or maybe, and this is darker, it's doing nothing. Maybe the signal hypothesis is us projecting our own communication paradigms onto something that operates on principles we don't understand. Maybe the coma is just a side effect of propulsion, and we're seeing patterns where none exist. The human brain is wired to find signals in noise. It's a survival trait, but it also makes us vulnerable to false positives. We see faces in clouds, hear voices in static, and detect intelligence in chaos. So the coma as antenna theory is tantalizing, but unproven. It's a narrative device more than a scientific conclusion. But narratives matter. They shape how we think about data, how we design observations, how we interpret ambiguity. And right now, the narrative around 3i Atlas is shifting. From weird comet to possible probe, from natural anomaly to potential signal. And that shift, even if it's premature, even if it's wrong, is forcing us to ask bigger questions. Questions about probability, about likelihood, about whether the universe is empty or full. And probability is where we go next. Because when you calculate the odds of 3i Atlas doing everything it's doing by accident, by chance, the numbers become unsettling. And if the odds are low enough, if the coincidences stack high enough, then maybe, just maybe, accident isn't the right explanation. Part 9. The Hill Radius Puzzle and Probabilistic Impossibilities. Let's talk about Jupiter's Hill sphere again, because this is where probability meets trajectory and things get weird. The Hill radius is the distance from a planet where its gravitational influence dominates over the sun's. For Jupiter, that's about 53 million kilometers, roughly 0.35 astronomical units. If you're trying to enter orbit around Jupiter, you want to get inside that radius, because that's where you can execute maneuvers efficiently, where Jupiter's gravity does the work for you. Now, 3i Atlas is predicted to pass close to Jupiter's Hill sphere on March 16th, 2026. Proponents of the artificial hypothesis argue this is not coincidence. They claim the object has been using periodic outgassing, those 16-hour pulses, to fine-tune its trajectory, to steer. And the target of that steering is Jupiter, specifically the Hill sphere. Because if you're an interstellar probe, if you're exploring a new solar system, Jupiter is where you want to be. It's the gravitational anchor, the hub, the most interesting destination outside the inner planets. Let's break down the probabilities. Start with the base rate. How often do interstellar objects pass through the inner solar system? Based on current detection rates, maybe a few per year, though most go undetected. Of those, how many pass close enough to Jupiter's Hill sphere to be considered a near encounter? That depends on the trajectory distribution, but it's a small fraction. Most hyperbolic orbits don't intersect planetary orbits at all. They skim through the system at high inclination or large perihelion distances and leave. So the odds of a random interstellar object passing near Jupiter's Hill sphere are low. Not impossible, but low. Now add the other anomalies. The object exhibits periodic outgassing with a stable 16-hour cycle. That's unusual. Most comets don't show such regularity. The object has a sunward jet, contradicting typical comet behavior. The object's light curve is dominated by coma luminosity, not reflected light from the nucleus. Each of these is individually odd. Combined, they're a pattern. Now here's the uncomfortable math. If each anomaly has, say, a 10% probability of occurring by chance in a random interstellar object, and you have 5 independent anomalies, the cumulative probability is 0.1 to the 5th power. That's 1 in 100,000. And if the Jupiter encounter is also unlikely, maybe 1 in 100, you multiply again. Now you're at 1 in 10 million. And we've only detected a handful of interstellar objects total. The odds of seeing this by chance, in our tiny sample, become vanishingly small. Of course, these probabilities are made up. I don't have precise numbers. Nobody does. But the qualitative point stands. When you stack unlikely events, the cumulative improbability grows exponentially. At some point, you have to seriously consider that what looks like coincidence might actually be causation. That the anomalies aren't independent accidents but features of a design. And here's the key insight. You don't need high thrust to navigate. If you have millions of years, if you're crossing interstellar space at tens of kilometers per second, even tiny velocity changes compound into massive positional changes. A delta V of 1 meter per second, applied early in the journey, can shift your arrival point by millions of kilometers. So if 3i Atlas has been using periodic burns to steer, if each 16-hour pulse is a course correction, then the object could have been aimed at Jupiter millions of years ago, and every burn since has been a tweak, a refinement, keeping the trajectory on target. This is speculative. I want to be clear about that. We don't have direct measurements of non-gravitational acceleration consistent with steering. We don't have telemetry. We don't have a smoking gun. But the circumstantial evidence is piling up, and when you look at the trajectory, when you see where it's going, when you calculate the odds, the artificial hypothesis stops looking crazy. It starts looking plausible. And if it's plausible, if there's even a chance that 3i Atlas is navigating, then the implications are staggering. Because navigation implies intent. Intent implies design. Design implies intelligence. And intelligence implies we are not alone. That somewhere out there, across the vast empty dark, someone built this object and sent it here, to explore, to observe, to report back, or maybe to do something we haven't even considered. And if that's true, then 3i Atlas isn't just an anomaly. It's a messenger, a signal, a first contact, not with flesh and blood beings, but with their technology, their legacy, their question to the universe. Are you out there? Are you listening? Are you ready? But before we get too far ahead of ourselves, let's remember that this isn't the first time strange objects have behaved strangely. History is full of anomalies, unexplained accelerations, comet mysteries that were never quite resolved. And if we're reconsidering 3i Atlas, maybe we should reconsider those older cases too, because patterns have a way of revealing themselves once you know what to look for. Part 10. Historical Echoes, Past Claims of Accelerating Objects. 3i Atlas is not the first object to exhibit unexplained non-gravitational accelerations. It's not the first comet to behave oddly, to fragment mysteriously, to brighten or dim in ways that strain natural models. History is littered with these cases, filed away in observatory archives, published in obscure journals, mentioned briefly in textbooks, and then forgotten. But if we're taking 3i Atlas seriously, If we're entertaining the possibility that it might be artificial, then maybe we should revisit those older mysteries. Because what if some of them were misinterpreted? What if they weren't comets at all? Let's look at a few examples. Comet Encke, discovered in 1819, has a well-documented history of non-gravitational accelerations. Its orbit decays faster than gravitational perturbations alone can explain. The standard explanation is outgassing, jets producing thrust. Fine. But Encke's activity is erratic, and the accelerations don't always match the expected direction or magnitude. Maybe it's just a complicated comet. Or maybe there's something else going on. Something we didn't notice because we weren't looking for it. Or consider certain near-Earth asteroids that exhibit low-level activity, faint comae, transient brightening, objects that sit on the boundary between asteroid and comet, classified as active asteroids or main belt comets. Some of these show periodic behavior, some fragment unexpectedly, some accelerate. We usually explain these as dormant comets reactivating, subsurface ice finally exposed after millions of years. But what if some of them aren't natural? What if they're derelict probes, ancient, damaged, still intermittently operational? I'm not saying that's the case. I'm saying we should be humble. We should recognize that our classification system, asteroid versus comet, natural versus artificial, is based on limited data and anthropocentric assumptions. We expect rocks and ice. We expect chaos and randomness. We don't expect machines. So when we see behavior that could be interpreted as mechanical, we default to natural explanations no matter how strained. But 3i Atlas is forcing a re-evaluation. And if we accept that it might be artificial, then we have to ask, how would we know? What would an artificial object look like from a distance with current observational tools? It might look exactly like a weird comet, outgassing, reflecting light, fragmenting under stress. The only way to tell the difference would be to look for patterns, regularity, coherence, intent. And when you start looking for patterns, you find them. Maybe you find them where they don't exist, because humans are pattern-seeking animals, or maybe you find them because they're real, and we've been ignoring them for centuries. There's a famous case from the 1970s, a small body that passed near Earth and exhibited highly unusual spectral properties and rotation. Observations were inconclusive, and the object was eventually lost, never recovered. Decades later, some researchers suggested it might have been space debris, a fragment from a lunar mission. Others argued it was a natural asteroid with unusual composition. But a very few, quietly wondered if it might have been something else, a probe, a visitor, and because we couldn't get better data, we'll never know. That's the frustrating thing about these historical cases. The data is ambiguous, the observations are incomplete, and by the time we realize something is interesting, it's already gone. Oumuamua was like that. We detected it on its way out of the solar system, and by the time we understood how weird it was too far away to study. We'll never know what it really was, but 3i Atlas is still here. It's approaching perihelion. It's heading toward Jupiter. We have time, we have telescopes, we have the opportunity to gather data, to test hypotheses, to figure out what this thing is before it leaves. And if it is artificial, if it is a probe, then this is the most important astronomical discovery in human history. Not because it proves aliens exist, but because it proves they're here, watching, waiting, and maybe, just maybe, hoping we're smart enough to notice. So the historical cases matter. They provide context. They show that anomalies aren't new, that strange behavior has always existed at the edges of our data. But they also show that we've been reluctant to consider the artificial hypothesis, even when natural explanations fail. And maybe that reluctance has cost us. Maybe we've missed signals because we weren't ready to see them. 3i Atlas is a second chance. Or maybe a third if you count Oumuamua. And if we're smart, if we're brave, we won't let this one slip away. We'll watch it. We'll measure it. We'll listen. And we'll see where it goes. Because March 2026 is coming, and whatever happens when 3i Atlas reaches Jupiter is going to be interesting. One way or another, we're going to learn something. And maybe, just maybe, that something will change everything. Part 11, 2025. When physics itself started leaning strange. Echoes from quantum gravity experiments. We need to talk about 2025, because it's been a strange year for physics. Not just astronomy, physics itself, foundations, the stuff we thought we understood, the rules we thought were fixed. And if those rules are starting to bend, if the universe is more flexible than we assumed, then maybe objects like 3i Atlas, aren't as impossible as they seem. There's been a series of tabletop experiments, small-scale, low-energy, exploring the interface between quantum mechanics and gravity. These aren't particle colliders. These are precision measurements of entangled systems, tests of locality, attempts to see if space-time itself exhibits quantum behavior. And some of the results, preliminary, not yet fully replicated, suggest that space-time might not be fundamental, that it might be emergent, that it arises from something deeper, something weirder. Quantum entanglement, information, correlations between events that shouldn't be correlated under classical physics. This is cutting-edge stuff, speculative, controversial. But it's part of a broader trend. For decades, physicists have been trying to reconcile quantum mechanics and general relativity, the two great theories of the 20th century that refuse to play nicely together. And one of the ideas that's gained traction is that space-time isn't a stage where physics happens, it's an illusion, a useful approximation that emerges from quantum interactions. And if that's true, if space-time is emergent, then the rules might be different than we think, more flexible, more manipulable. Why does this matter for 3i Atlas? Because if an advanced civilization understands this, if they've figured out how to engineer space-time at small scales, then propulsion becomes a different game. You're not just pushing against reaction mass. You're not bound by the tyranny of the rocket equation. You're manipulating the structure of space itself, and that opens up possibilities that look like magic from our perspective. Low-thrust, high-efficiency engines, shielding against interstellar radiation, maybe even faster than light travel if you believe the most optimistic interpretations. I'm not saying 3i Atlas is using any of this. I'm saying the scientific Overton window is shifting. What seemed impossible 10 years ago is now being seriously discussed in peer-reviewed journals. And that shift in what's considered possible changes how we interpret anomalies. Because if our models of reality are incomplete, if there's physics we haven't discovered yet, then maybe some of what we see as violations of natural law are actually natural. Just natural in a framework we don't yet understand. And here's the philosophical kicker. We've always assumed that the laws of physics are universal, that what works here works everywhere. And maybe that's true. But maybe our formulation of those laws is parochial, solar system-centric, based on experiments done at room temperature, at low velocities, in weak gravitational fields. What happens at extremes? What happens in the vast empty dark between stars, where objects drift for millions of years bathed in cosmic rays, subjected to pressures and conditions we can't replicate in a lab? Maybe interstellar objects, whether natural or artificial, operate under regimes we don't understand. Maybe their chemistry is different, their physics is different, and maybe, when we see something like 3i Atlas, something that doesn't fit our models, we shouldn't default to weird comet. We should default to unknown, and then we should investigate, openly, without prejudice. Because the universe doesn't care about our comfort. It is what it is. And if it's stranger than we thought, that's not a problem. That's an opportunity. So, the quantum gravity experiments, the hints of emergent space-time, they're not directly related to 3i Atlas, but they're part of the same story. The story of 2025, the year when science started questioning its foundations, when anomalies piled up, when the universe stopped making sense in the old ways, and when people started wondering, seriously wondering, if maybe we've been missing something big. And it's not just physics. Chemistry is having its own reckoning. Because in 2025, AI discovered something that shouldn't exist. A molecule, stable, high energy, predicted by no theory, synthesized in no lab, until now, and that discovery is making chemists very, very uncomfortable. Part 12. The AI discovered molecule that shouldn't exist. Imagine a molecule, a specific arrangement of atoms, bonds, electrons, and imagine that this molecule has properties that make no sense. It's stable, but it shouldn't be. The energy configuration is wrong. According to everything we know about quantum chemistry, about molecular orbital theory, about the way electrons fill shells and form bonds, this molecule should tear itself apart instantly. The bonding geometry violates textbook rules. Atoms positioned too close together, or too far apart, or at angles that contradict VSEPA theory. And yet, it exists. Because an AI system, trained on vast databases of chemical structures and reaction pathways, predicted it. And then, because humans are curious and slightly reckless, someone synthesized it. And it worked. The molecule didn't explode. It didn't decompose into simpler, more stable compounds. It sat there, in a flask or on a substrate, stable at room temperature, defying expectations. Researchers could study it, measure its properties, confirm its structure, and every measurement said the same thing. This shouldn't exist, but it does. This happened in 2025. Multiple research groups using AI-driven molecular design platforms have reported discovering stable compounds that conventional quantum chemistry didn't predict. High-energy molecules that should decompose instantly but don't. Compounds with strained rings, unusual oxidation states, exotic bonding patterns that shouldn't be possible under standard valence theory. Materials with unusual optical or electronic properties that have no precedent in the literature. Molecules that absorb light at unexpected wavelengths, conduct electricity in strange ways, exhibit magnetic properties that don't match their electron configurations. The AI didn't care about rules, it cared about energy landscapes. It explored vast regions of chemical space that human chemists never thought to investigate, either because the compounds looked too unstable, too complicated, too implausible. But the AI, free from bias and prejudice, evaluated millions of possibilities. It calculated quantum mechanical properties, assessed stability, predicted synthesis routes, and occasionally it found configurations that were stable, not just metastable, not just kinetically trapped, but genuinely stable. Local minima in the energy landscape that quantum chemistry predicts should exist, but that human intuition never identified. The implications are unsettling. Because chemistry, like astronomy, is built on models, we think we understand how atoms bond, how molecules form, how reactions proceed. We have the periodic table, we have valence shell electron pair repulsion theory, we have molecular orbital theory, we have thermodynamics and kinetics. We've tested those models exhaustively, in laboratories around the world, for over a century. And they work. Mostly. But mostly isn't always. And when AI starts finding exceptions, when it discovers molecules in parameter space we never explored, it reveals that our chemical intuition is incomplete. That our models, while useful, while predictive for the compounds we've already synthesized, don't capture the full range of what's possible. That there are stable configurations out there, waiting to be found, that we never imagined. Molecules that nature on Earth never produced, because the formation pathways never occurred, because the temperatures or pressures or catalysts weren't right. But that could exist, given the right conditions. And if our models of chemistry, developed through centuries of careful experimentation, are incomplete, what does that say about our models of other phenomena? Our models of comets, our models of interstellar objects, our assumptions about what's natural and what's artificial. Now let's connect this to 3i Atlas. Comets are chemistry. They're not abstract astrophysical phenomena. They're physical objects, made of atoms and molecules, governed by chemical reactions. They're mixtures of water ice, carbon dioxide, methane, ammonia, silicates, complex organics. We know what comets are made of because we've studied solar system comets extensively. We've sent missions, Giotto to Halley, Stardust to Wild 2, Rosetta to 67 P. Churyumov-Gerasimenko. We've measured their composition with mass spectrometers. We've mapped their volatiles with infrared spectroscopy. We've collected dust samples and returned them to Earth. And based on that data, we have a template. This is what a comet looks like. This is what cometary chemistry is. But what if interstellar comets are different? What if they formed in environments with different temperatures, different radiation fields, different chemical precursors? What if they condensed in molecular clouds with unusual compositions, enriched in heavy elements or depleted in volatiles? What if they orbited stars with different spectral types, experiencing different UV radiation during their formation? What if they spent billions of years in interstellar space, bombarded by cosmic rays, undergoing radiolysis, accumulating chemical damage and alteration? What if they contain molecules we've never seen, compounds that are stable in deep space, at temperatures near absolute zero, under constant radiation, but exotic by our standards? Compounds that our Earth-based chemistry, our room temperature, 1 atmosphere, water-based intuition wouldn't predict. And what if those exotic compounds give rise to behaviors we don't expect? Unusual sublimation rates, because the binding energies are different. Strange emission spectra, because the electronic transitions don't match known molecules. High energy outbursts because metastable compounds suddenly decompose, releasing stored energy. We've already seen hints of this. Observations of 3I Atlas show high carbon dioxide to water ratios, higher than typical solar system comets. That could indicate formation in a colder environment, farther from its parent star, where CO2 ice is more stable relative to water. The spectral slope suggests D-type composition, primitive and carbon-rich, different from the ultra-red trans-Neptunian objects. There's evidence of cosmic ray processing, surface alteration from radiation damage. All of this suggests chemistry that's different from what we're used to. Not impossible, not artificial, just different. But there's a line, a boundary between different chemistry and impossible chemistry. And when you cross that line, when the observations require compounds or reactions that our models say shouldn't exist, you have two options. Option 1, your models are wrong, incomplete. There's chemistry out there, natural chemistry, that operates under principles we haven't discovered yet. Option 2, what you're looking at isn't natural, it's engineered. Or, and this is the speculative leap, what if an artificial object uses exotic chemistry? What if you're not limited to naturally occurring compounds, to molecules that form spontaneously in stellar nurseries or cometary nuclei? What if you can design molecules, use AI or alien equivalent computational tools to explore chemical space exhaustively, to find the optimal compounds for your purposes? High-energy fuels that are stable in storage but release enormous energy when decomposed. Propellants with specific impulses far exceeding anything we've synthesized. Materials with unusual thermal or optical properties that create the observed brightness variations. Substances that absorb solar radiation efficiently and re-emit it at specific wavelengths, modulating the signal. Compounds that scatter or amplify electromagnetic radiation, supporting the coma as antenna hypothesis. Exotic ices that sublime rhythmically, creating periodic outbursts, not because of thermal cycling or pressure buildup, but because their decomposition pathways are engineered to pulse. If you're building an interstellar probe, you're not limited to water and methane. You're not constrained by what nature provides. You're using the best materials chemistry can provide. And if your civilization has mastered AI-designed molecules, if you've explored parameter space far beyond what nature stumbled upon during planetary formation, if you've had millions of years to refine your material science, then your probe might be made of stuff we wouldn't recognize. Stuff that looks natural, that fits within the laws of quantum mechanics and thermodynamics, but that's optimized, designed, engineered. And from a distance, with limited spectroscopy, with low signal-to-noise observations, we might not be able to tell the difference. We'd see outgassing, we'd see brightness variations, we'd measure compositions, and we'd say it's a comet. A weird comet, yes, but a comet. Because we don't have reference spectra for AI-designed exotic molecules. We don't know what engineered chemistry looks like. We've never seen it before. This is all speculation. But it's informed speculation. Because we now know that our chemical models are incomplete, that AI can find molecules we didn't predict, that there are vast regions of chemical space we've never explored, filled with stable compounds we've never imagined. And if we, with our primitive 2025 AI, can already do that, if we can already discover molecules that violate our textbook rules, imagine what a civilization a million years more advanced could do. Imagine the materials they'd have. Structures with properties we can't conceive. Superconductors that work at room temperature. Transparent metals. Programmable matter that reconfigures itself. Compounds that store energy at densities approaching nuclear fuel. Materials that self-repair, that adapt to environments, that grow and evolve. The chemistry they'd command. Reactions we've never written. Catalysts we've never synthesized, processes that transform matter in ways that look like magic to us, and how utterly alien their artifacts would appear. Not necessarily visually, not glowing or pulsing with impossible colors, but chemically, spectrally, compositionally. When you analyze them, when you try to fit them into your models, they don't fit. The molecules are wrong, the reactions are wrong, the energetics are wrong, and you're left with a choice. Admit your models are incomplete, that chemistry is bigger than you thought, or admit that what you're looking at was made, designed, built by someone who understands chemistry better than you do. So when we see 3I Atlas outgassing strange mixtures, when we detect high CO2 to H2O ratios, when the spectral slopes don't quite match known objects, when the brightness variations require mechanisms we don't fully understand, maybe the answer isn't that it's a weird comet. Maybe the answer is that it's made of weird chemistry we don't understand, chemistry that expands what's possible, chemistry that might be natural, might be the result of exotic formation conditions and interstellar processing, or chemistry that might be artificial, the product of molecular design and engineering far beyond our capabilities. And if that's true, then natural and artificial start to blur. The boundary becomes fuzzy, because if nature can produce molecules we never imagined, molecules that AI discovers in chemical space we never explored, then maybe nature can produce objects that look engineered, objects with regular behavior, with optimized properties, with signatures that scream design. Or maybe engineering, sufficiently advanced, produces objects that look natural, that blend in, that mimic comets or asteroids or debris, indistinguishable without close examination. And the only way to tell the difference is to look closer, to measure better, to get resolved spectroscopy, to identify specific molecules, to compare them against databases and models and AI predictions, to send probes, if we can, to sample the coma directly, to analyze the chemistry in situ, to stop assuming we know what's possible, what's natural, what's reasonable. Because chemistry, as we're learning in 2025, is far stranger than our textbooks suggested. The periodic table is just the beginning. The compounds we've synthesized, the reactions we've studied, they're a tiny fraction of what exists, what could exist. And out there in interstellar space, in objects drifting through our solar system, there might be chemistry we've never dreamed of, natural or artificial, exotic or engineered. And until we look, until we measure, until we let go of our assumptions and embrace the possibility that we don't know everything, we'll never find out. Which brings us to fusion, because in 2025, fusion energy finally started to work. And that changes everything, not just for power generation, for propulsion, for interstellar travel, for understanding what's possible, and for recognizing that what we're seeing in 3i Atlas might not be chemistry at all. It might be physics, the physics of controlled fusion, the signature of an engine. Part 13. Fusion's Breakthrough Year. Periodic Power and the Engine Analogy. December 5th, 2022. Scientists at the National Ignition Facility in California achieve fusion ignition, more energy out than in. For a brief moment, a tiny capsule of hydrogen becomes a star. The fuel pellet, smaller than a peppercorn, is bombarded by 192 laser beams, delivering over 2 million joules of energy. The hydrogen atoms compress, heat to millions of degrees, and fuse. And in that instant, that fraction of a second, the reaction releases more energy than the lasers delivered. Net positive energy, ignition, the holy grail of fusion research pursued for 70 years, finally achieved, and in 2025 they did it again and again and again, repeatedly, reliably, with engineering improvements that suggest we're on the verge of actual fusion power. Not 50 years away, the perpetual promise that's haunted fusion research since the 1950s. Not sometime in the future. Now. The repetition rate is increasing. The energy gain is improving. The target fabrication is becoming cheaper. The laser systems are becoming more efficient. All the engineering challenges that stood between a one-time demonstration and a practical power source are being solved one by one. Fusion reactors don't burn continuously, they pulse. You compress the fuel, heat it, ignite the reaction. The fuel fuses, releases energy in a burst of neutrons and heat. Then you cool down, reset, and do it again. It's a cycle, a rhythm. And the timing of that cycle depends on the engineering. How fast you can inject fuel, how quickly the reactor can dissipate heat without damaging the chamber walls, how much energy you can extract per pulse before diminishing returns set in, how rapidly you can recharge the laser or magnetic confinement systems. For terrestrial power plants, you want high repetition rates, pulses every second or faster, to generate continuous electricity. The reactor fires, heats water or another working fluid, drives turbines, generates power, then it fires again and again. You need that continuity, that steady output to feed into the electrical grid. Interruptions, gaps, irregular pulses, those are problems. They require batteries, capacitors, backup systems. So engineers are pushing for faster cycles, smoother operation, approaching the continuous burn that other power sources provide. But for propulsion, especially interstellar propulsion, the requirements are different. Fundamentally different. You're not trying to generate electricity, you're trying to generate thrust. to eject mass at high velocity and use the reaction force to accelerate your spacecraft. And for that, continuous operation isn't necessary. In fact, it might not even be desirable. Imagine a fusion engine aboard a spacecraft. You don't need continuous thrust. You need periodic burns, pulses. You fuse a small amount of fuel, eject the plasma out a magnetic nozzle, generate thrust. The plasma, moving at thousands of kilometers per second, carries momentum. The spacecraft recoils in the opposite direction. Newton's third law scaled up to fusion energies. Then you wait. Let the reactor cool. Let the magnetic coil stabilize. Conserve fuel, and then you pulse again. The interval between pulses depends on your mission profile. If you're accelerating, building up velocity for an interstellar journey, you might pulse frequently. Every few minutes, every hour, burning through fuel quickly but efficiently, maximizing thrust while your propellant lasts. If you're coasting already at cruise velocity, you might pulse once per day or once per week, just to maintain course, to correct for gravitational perturbations or interstellar drag. And if you're navigating, if you're fine-tuning your trajectory to hit a specific target across light years, you might pulse on a very specific schedule, a duty cycle. Carefully timed burns, executed with precision, each one calculated to adjust your path by fractions of a degree, to bring you to your destination millions of years hence. Sound familiar? Because that's exactly what we see with 3i Atlas, a 16.1 6-hour cycle. Regular, predictable. Each pulse produces a massive outflow of gas and dust, creating a glowing coma tens of thousands of kilometers wide. Then the object goes quiet. The coma fades, the brightness drops, and 16 hours later it pulses again. Same amplitude, same duration, same pattern. If you wanted to design a fusion-powered interstellar probe, this is what it might look like. This is the observational signature you'd expect. Now, I'm not claiming 3i Atlas uses fusion. We have no direct evidence of that. No detection of fusion byproducts, no neutron signatures, no gamma rays, no diagnostic lines in the spectrum that would scream fusion plasma. But the conceptual parallel is striking, almost unnervingly so. Because fusion is the most plausible propulsion technology for interstellar travel. It's energy dense. A single kilogram of fusion fuel, deuterium and tritium or deuterium and helium-3, contains as much energy as tens of thousands of tons of chemical propellant. It's fuel efficient. The exhaust velocity, the speed at which plasma exits the engine, can reach thousands of kilometers per second, orders of magnitude faster than chemical rockets. And it's within the realm of known physics. We don't need exotic matter or negative energy or warp drives or any of the speculative physics that might or might not be possible. We just need to compress hydrogen and make it fuse, heat it, squeeze it, push the nuclei together until the strong force overcomes electrostatic repulsion and binds them into helium. And in 2025, we've proven we can do that, not just once, repeatedly, with improving efficiency and control. So if a civilization somewhere out there wanted to send probes across the galaxy, fusion is the obvious choice. You pack your probe with deuterium or helium-3, mined from gas giants or manufactured in stellar factories. You install a compact reactor miniaturized and hardened to survive millions of years in the radiation-soaked void of interstellar space. You add guidance systems, sensors, communication arrays, maybe AI or programmed instructions to handle navigation and decision-making, and you send it on its way. It pulses periodically, maintaining trajectory, adjusting course as needed, operating for millions of years on a single fuel load, because in space there's no friction, no air resistance, velocity is free. Once you're moving, you keep moving. You only need thrust for course corrections, for deceleration, for entering orbit around a target star or planet. So your fuel can last effectively forever, if you're careful, if you pulse sparingly, if you operate on a duty cycle. And from a distance, from Earth, what would that look like? It would look like a comet, periodic outgassing, brightness variations, a glowing coma, except it wouldn't be ice sublimating. It would be plasma venting, ionized hydrogen and helium, ejected at high velocity, scattering sunlight, glowing from residual thermal energy and recombination radiation. And the difference, unless you look very closely, unless you have high-resolution spectroscopy and can distinguish between water vapor and ionized plasma, might be hard to spot. This is why 3i Atlas is so important. Because we're now at a point where our own technology is converging with what we might expect from an alien probe. Fusion propulsion is no longer science fiction. It's no longer a distant dream relegated to speculative novels and far future scenarios. It's engineering, it's happening, we're building it, and that means we can make concrete predictions about what such a probe would look like, how it would behave, what observational signatures it would produce, and then we can compare those predictions to what we see. And what we see in 3I Atlas is disturbingly consistent with the fusion hypothesis. The periodicity, the amplitude, the scale of the coma, the jet geometry if those jets are directed plasma exhaust rather than random sublimation, the trajectory, possibly shaped by non-gravitational accelerations from thrust. Not proof. We need more data, better spectroscopy, resolved imaging, direct detection of fusion signatures, but consistent, alarmingly consistent. And consistency, when combined with all the other anomalies, the coma dominance calculation, the sunward jet, the Jupiter trajectory, builds a case. A circumstantial case, yes, but a case nonetheless. The breakthrough in fusion matters for another reason. It signals a shift in human capability. For the first time, we're building technologies that could, in principle, be used for interstellar travel. Not today, not next year. But within a century or two, if we don't destroy ourselves, if we survive climate change and resource wars and political instability, if we keep advancing, keep building, keep dreaming, we might be launching our own probes, our own scouts. Project Breakthrough. Starshot, proposed in 2016, aims to send lightweight probes to Alpha Centauri using laser-driven light sails. That's one approach. But fusion offers another. Heavier probes, more capable, carrying more instruments, more shielding, more fuel for maneuvering. Probes that could decelerate at the target system, enter orbit, deploy sub-probes to explore planets and moons. Probes that look, functionally, a lot like what we imagine 3I Atlas might be. And when we do launch them, when humanity finally sends its emissaries to the stars, they'll pulse, they'll navigate, they'll explore, they'll transmit data back home, across light years, patient signals carrying measurements and images and discoveries, and some distant civilization, if they're watching, if they have telescopes and curiosity and the wisdom to look, will see them and wonder, are those natural or artificial? Are we alone, or is someone out there? They'll face the same questions we're facing now, the same ambiguity, the same challenge of distinguishing between a weird comet and a technological artifact. And maybe they'll be braver than we are. Maybe they'll accept the evidence faster, without the decades of denial and skepticism and caution that plague our scientific culture. Or maybe they'll be more skeptical, more conservative, more committed to natural explanations. We'll never know. Unless, of course, they respond. Unless they try to make contact. Unless they're as curious about us as we are about them. So fusion, in 2025, isn't just an energy breakthrough. It's not just about solving our power problems, replacing fossil fuels, mitigating climate change, building a sustainable civilization. It's a mirror, a reflection of what might already be here, drifting through our solar system, watching us figure it out, watching us take our first stumbling steps toward becoming an interstellar species, watching us build the same technologies they built, however many millions of years ago. And maybe, if 3I Atlas really is a probe, if it really is artificial, it's been waiting for this. Waiting for us to reach a threshold of technological maturity, waiting for us to build fusion reactors, to understand propulsion physics, to be capable of recognizing what it is. Because contact, if it happens, has to be mutual. Both sides have to be ready. And maybe we're finally ready. Maybe 2025 is the year we're ready. Or maybe we're still decades away. Maybe 3I Atlas will come and go, and we'll still be arguing about whether it's natural or artificial, and we'll miss the opportunity. We'll let it slip away, just like we let Oumuamua slip away. And we'll be left with questions, regrets, endless debates about what we should have done. But at least now, with fusion becoming real, we have a framework, a reference point. We can say, if we were building an interstellar probe, this is how we'd do it. And this is what it would look like. And this is what 3I Atlas looks like. And the resemblance is uncanny. And it's not just fusion. AI is rewriting the rules too. Not just in chemistry, in physics. Because in 2025 we started letting AI do physics, and the results are both thrilling and terrifying. Because when you give machines the power to discover new laws, to invent new theories, to model reality in ways human minds can't grasp. You open a door, and you don't know what's on the other side. You don't know if you'll understand what you find, or if understanding even matters anymore. Part 14. The Rise of Self-Evolving AI Physics Engines, Rewriting the Rules on the Fly. Physics is about models. We observe nature, we find patterns, we write equations that describe those patterns. Newton's laws, Maxwell's equations, Einstein's relativity, quantum, mechanics. These models work because they capture underlying truths about how the universe operates. But they're still models, simplifications, approximations, and sometimes they fail. When Newton wrote his laws of motion, he wasn't describing reality directly. He was building a mathematical framework that predicted how objects move under the influence of forces, and it worked brilliantly. For 2 centuries, Newtonian mechanics was the foundation of physics. It sent us to the moon. It built bridges and satellites and entire civilizations. But then we looked closer. We measured light from distant stars, we studied atoms, we pushed velocities toward the speed of light. And Newton's laws broke down. They were still useful, still accurate at everyday scales, but they weren't fundamental. They were approximations of something deeper. Einstein's relativity. And then Einstein's equations, beautiful and powerful as they are, started showing cracks too. They can't describe what happens inside a black hole. They can't reconcile with quantum mechanics. They predict singularities, infinities, places where the math breaks and reality becomes undefined. So we know relativity is also an approximation. A very good one, but not the final word. Somewhere beneath it, or beyond it, there's another layer, another model waiting to be discovered. Traditionally, when a model fails, we adjust it. We add terms, we refine parameters, we build more complex theories. We introduce new fields, new particles, new dimensions. String theory, loop quantum gravity, modified gravity theories. The process is slow, painstaking, requiring human intuition, creativity, years of trial and error. A physicist spends a career building a theory, testing it against data, refining it until it works or abandoning it if it doesn't. This is how science has always progressed, slowly, carefully. Human minds wrestling with equations, searching for patterns, guided by intuition and experience. But in 2025, something changed. We started offloading that process to AI. We're feeding observational data into machine learning systems and asking them to find the patterns, to generate the models, to evolve the physics, not to simulate what we already know, but to discover what we don't, to explore theoretical possibilities we haven't imagined, to test combinations of parameters we'd never think to try, to build models from the ground up based purely on what the data demands. These aren't traditional simulations, these are self-evolving engines, AI systems that don't just model known physics, they invent new physics. They create internal rule sets, equations, interactions that match the data, even if those rule sets don't correspond to any theory we've written. The AI doesn't care about elegance or mathematical beauty, or whether its equations make intuitive sense. It cares about fit, about prediction, about minimizing error between model and observation, and sometimes those AI-generated models work better than ours. They predict observations we couldn't. They explain anomalies that baffled human physicists. They find connections we missed, symmetries we overlooked, dependencies we didn't consider. In fields like particle physics, material science, quantum chemistry, AI is already outperforming traditional theoretical approaches. It's finding ground states of complex systems, predicting molecular properties, optimizing quantum circuits, solving problems that would take human researchers decades. This is both powerful and dangerous. Powerful because it lets us explore parameter space far beyond human intuition. There are billions of possible physical theories, most of them wrong, but some of them potentially right in ways we haven't considered. Human physicists can explore maybe dozens in a career. AI can explore millions. It can test theories we'd dismiss as crazy, combinations of effects we'd never think to combine, regimes we'd assume were impossible. And occasionally it finds something that works. But it's dangerous because we lose interpretability. The AI's model might work, but we don't understand why. It's a black box, a mathematical abstraction that fits the data but doesn't illuminate the underlying mechanism. We gain predictive power at the cost of insight, and physics isn't just about prediction, It's about understanding, about building intuition, about knowing not just what will happen, but why it happens. And when an AI hands us an equation with 200 terms, each one a complicated function of variables we can't visualize, we're left in a strange position. The model works, but we don't understand it. Do we trust it anyway? Do we use it to make predictions, to guide experiments, to build technology, even if we can't explain the physics behind it? Or do we insist on understanding, even if that means accepting less accurate models? This is the epistemological crisis emerging in 2025. Our tools are becoming more capable than we are, and we're being forced to decide whether understanding matters more than accuracy. Now, apply this to 3i Atlas. Imagine feeding all the observational data into an AI physics engine. The light curve, with its precise 16.16-hour periodicity and large amplitude variations. The spectroscopy, showing unusual compositional ratios and spectral slopes. The trajectory, hyperbolic but potentially intersecting Jupiter's Hill sphere. The jet geometry, including that problematic sunward component. The coma dynamics, the brightness dominance, the structural constraints. Everything. Every data point, every measurement, every uncertainty. And you ask the AI, what model explains this? You give it freedom to explore any physical mechanism. Comet models, yes, but also exotic ices, pressure-driven eruptions, radiation effects, electromagnetic interactions, plasma dynamics, even propulsion systems. You let it consider natural and artificial scenarios without prejudice. You just ask, what fits? And maybe the AI comes back with something unexpected. Not a simple rotating comet, not a standard propulsion system, but something else. A hybrid, a mechanism that involves exotic matter we haven't synthesized, or weakly interacting fields we haven't detected, or thermodynamic cycles that operate under conditions we've never studied. Maybe it proposes that the nucleus contains metastable compounds that release energy through mechanisms we don't fully understand. Maybe it suggests that the coma isn't just gas and dust, but includes plasma structures, magnetic fields, ionization effects that create the observed brightness patterns. And maybe that model fits perfectly. Maybe it predicts behaviors we can test. Specific spectral lines at certain wavelengths. Variations in the light curve that should occur as the object approaches perihelion. Changes in the jet structure as solar radiation pressure increases. And maybe, when we test them, when we point our telescopes and look, they're confirmed. The predictions match reality. The AI was right. What do we do then? Do we accept the AI's model, even if we don't understand it? Do we trust a black box physics engine to tell us what's real? The model makes accurate predictions, which is the gold standard in science. But it doesn't give us insight. We can't explain to students why it works. We can't publish a paper that walks through the derivation step by step. We just have equations, complicated, opaque, effective equations that happen to match the data. Or do we reject it? Do we stick with human-derived models, even if they don't fit as well? Do we insist on understanding, on physical intuition, on theories we can explain and defend? And in doing so, do we risk missing the truth because it's too complex for human minds to grasp without computational assistance? This is the epistemological crisis of 2025. Our tools are becoming smarter than we are. They're finding patterns we can't see, building models we can't understand, making predictions we can't derive, and we're forced to decide how much we trust them, how much we're willing to surrender our need for understanding in exchange for accuracy. For 3i Atlas, this matters because the object is borderline. It's right on the edge of what natural models can explain. Human physicists using conventional approaches are struggling. The comet model doesn't quite work. The artificial model seems too speculative. We're stuck in ambiguity, unable to commit to either explanation with confidence. But an AI doesn't have that problem. It doesn't care about speculation or conservatism. It just evaluates fit. And if we let AI loose on the data, if we allow self-evolving physics engines to generate explanations, we might discover that the boundary between natural and artificial is fuzzier than we thought. Maybe there are physical regimes, exotic conditions found in interstellar space or in objects with unusual formation, histories, where matter and energy behave in ways that look engineered but aren't, where periodicity emerges from chaos, where regularity arises from complexity, where the signature of design appears even in purely natural systems. Or maybe, and this is equally unsettling, AI will confirm what some of us already suspect, that the data is consistent with technology, that when you strip away human bias, when you just look at the observations and ask what explains them most simply, the answer involves intent. The simplest model, the one that fits best, the one with the fewest free parameters and the highest predictive power, involves a propulsion system, a duty cycle, navigation. And if that happens, if an AI system, unbiased by human hopes or fears, uninfluenced by career concerns or philosophical preferences, concludes that 3i Atlas is probably artificial, what do we do? Do we believe it? Do we take the AI's conclusion seriously and act on it? Do we start preparing for contact, mobilizing resources, planning observations, developing communication strategies? Or do we dismiss it? Do we call it an overfit, a statistical fluke, a machine hallucinating patterns where none exist? Do we argue that the AI lacks physical intuition, that it's found a mathematical solution that's formally correct but physically meaningless? Do we insist that human judgment, human understanding, human wisdom still matters more than algorithmic accuracy? These are not hypothetical questions anymore. This is where we are in 2025. Our tools are evolving faster than our philosophy. Our models are being rewritten by machines, and objects like 3i Atlas are forcing us to confront the limits of our understanding. Because the universe doesn't care what we believe, it doesn't care about our need for understanding or our comfort with ambiguity. It is what it is. It follows laws, known or unknown, simple or complex, comprehensible or opaque. And if it's stranger, weirder, more alive than we thought, if the physics operating in interstellar space or in ancient objects or in civilizations millions of years more advanced is beyond our current grasp, then we need to adapt. We need to update our priors. We need to expand our conception of what's possible. We need to be humble enough to admit that maybe, just maybe, we've been wrong about a lot of things. We've been wrong before. We thought the Earth was the center of the universe. We thought space and time were absolute. We thought determinism ruled reality until quantum mechanics showed us probability and uncertainty. Every generation of physicists discovers that the previous generation's certainties were approximations, that reality is deeper, stranger, more subtle than we imagined. And 2025 might be another one of those moments, another paradigm shift, another humbling, and nowhere is that humility more needed than in cosmology. Because in 2025, the universe itself started looking strange, not just at the scale of comets and probes, at the scale of galaxies, dark matter, the fundamental structure of reality. And if our cosmological models are cracking, if the universe isn't what we thought, then maybe we need to rethink everything, including whether we're alone, including what's possible, including whether objects like 3i Atlas represent natural extremes or technological visitors. The AI might give us answers, but it won't give us certainty. It won't give us comfort. It will give us models, predictions, probabilities, and we'll have to decide what to do with them, whether to trust the machines or trust ourselves, whether to embrace complexity or demand simplicity, whether to accept that some truths might be knowable only through computation, not through human understanding. That's the future we're building, a future where physics is discovered by algorithms, where models are too complex for textbooks, where prediction is possible but explanation is not. It's unsettling, it's exciting, and it's happening right now with objects like 3i Atlas as the test cases. The universe is offering us mysteries, and we're building machines to solve them. The question is, will we understand the solutions, or will we just have to trust them? Part 15, the 2025 Dark Matter Anomaly Reopened, a Cosmic Humility Reflection. Dark matter has been a problem for decades. We know it's there because galaxies rotate too fast. Galaxy clusters hold together too well. Gravitational lensing reveals mass we can't see. So we infer the existence of dark matter, some form of non-interacting or weakly interacting mass that makes up 85% of the universe's matter content. And for years, we've been searching for it, building detectors, analyzing data, looking for the particle, the field, the whatever it is that explains the observations. But we haven't found it. Every detector comes up empty. Every experiment sets new limits. We dig deeper underground, build more sensitive instruments, wait longer for a signal that never comes. And in 2025, a reanalysis of dwarf galaxy rotation curves revealed something troubling. The data doesn't quite fit. Small-scale structure, the distribution of dark matter in the smallest galaxies deviates from predictions, not by much, but enough to matter, enough to suggest that our standard model, lambda cold dark matter, might be incomplete. These dwarf galaxies are important because they're simple, they're small, they're dark matter dominated, they don't have the complex star formation and feedback processes that complicate larger galaxies. They should be clean test cases for our dark matter models. And yet, when we measure how stars move in these galaxies, when we calculate how much mass must be present to explain those motions, the numbers don't match what our simulations predict. The dark matter distribution is smoother than expected, or clumpier or shaped differently. The details vary depending on which galaxies you look at, but the pattern is consistent. Something is off. Maybe dark matter behaves differently at small scales. Maybe it interacts with itself in ways we didn't predict, through forces we haven't discovered. Self-interacting dark matter models have been proposed, where dark matter particles can scatter off each other, redistributing mass in ways that change the structure of halos. Maybe it's not a single particle, but a spectrum of particles, a whole dark sector we haven't explored, with its own forces and interactions, a shadow universe overlapping ours but invisible except through gravity. Or maybe, and this is the option nobody wants to say, maybe dark matter doesn't exist. Maybe we're wrong about gravity. Maybe Einstein's equations, which have worked so brilliantly for a century, need modification at galactic scales. Modified Newtonian dynamics, MOND, and its relativistic extensions have been around for decades, dismissed by most physicists but never quite killed off. And every time dark matter searches come up empty, every time galaxy data doesn't quite fit, the alternative theories get a little more attention, a little more credibility. Maybe the universe is weirder than we thought. Maybe gravity doesn't scale the way we assume. Maybe there are additional fields, additional dimensions, additional effects that only manifest over vast distances or in weak gravitational regimes. Maybe our equations, derived from solar system observations and laboratory experiments, are accurate locally but break down globally. It wouldn't be the first time in physics that a theory we thought was universal turned out to be an approximation. This isn't directly related to 3i Atlas. But it's part of the same theme, the theme of 2025, the year when foundations cracked, when models failed, when anomalies piled up faster than explanations, and when scientists across disciplines started admitting that maybe we don't understand as much as we thought we did. In particle physics, in cosmology, in chemistry, in astronomy, everywhere you look there are cracks, data that doesn't fit, predictions that fail, experiments that contradict theory. And that's okay. That's how science works. We build models, we test them, they fail, we build better models. The process is iterative, cumulative, self-correcting, but it requires humility. It requires the willingness to say, I don't know, I was wrong, let's start over. And that's hard, especially when careers are built on specific models, when decades of research assume certain frameworks, when admitting uncertainty feels like admitting failure. But uncertainty isn't failure. Uncertainty is honesty. It's the recognition that our knowledge is provisional, that our theories are tools, not truths. And when the tools stop working, when the data stops cooperating, we need new tools, new frameworks, new ways of thinking. That's not a crisis. That's progress. Uncomfortable progress, yes, but progress nonetheless. 3i Atlas is part of that process. It's an anomaly, a challenge, a question mark. And whether it turns out to be natural or artificial, whether it's a weird comet or a probe from another civilization, the mere fact that we don't know is valuable, because it forces us to expand our thinking, to consider possibilities we dismissed, to look at the universe with fresh eyes, without the blinders of expectation and assumption. For decades, we've categorized objects: asteroid, comet, planet, star, natural, artificial, alive, dead. And those categories worked because the boundaries were clear. But what happens when you find something on the boundary, something that doesn't fit neatly into any box? You can force it into a category, squeeze it until it fits, ignore the parts that stick out. Or you can admit that maybe your categories are incomplete, that maybe nature or intelligence or whatever's out there doesn't respect the lines we've drawn. And maybe that's the real lesson here. Not that aliens exist, not that we found a mothership, but that the universe is vastly more complex, more strange, more unknowable than we've allowed ourselves to believe, that our models, for all their success, are still approximations. Useful approximations, yes. Models that let us predict eclipses, launch satellites, understand chemistry and biology and the structure of matter. But approximations nonetheless. Simplifications of a reality that's infinitely more intricate. There are phenomena out there we haven't categorized, mechanisms we haven't discovered, intelligences we haven't met. And maybe some of those phenomena operate on principles we don't understand. Maybe some of those mechanisms use physics we haven't formulated. Maybe some of those intelligences think in ways we can't imagine. And when we encounter them, when we try to fit them into our existing frameworks, we fail. Not because the frameworks are wrong, exactly, but because they're incomplete. 3i Atlas is heading toward Jupiter. In March 2026, it will make its closest approach, and we'll be watching, with telescopes, with spectrometers, with radio dishes and infrared cameras and every tool we have. And maybe we'll find answers. Maybe we'll confirm it's natural, a bizarre but understandable comet with exotic internal structure, unusual composition, improbable but possible under the right formation conditions. Maybe we'll trace the jets, map the coma, measure the nucleus, and discover that yes, it's just ice and rock, sublimating in strange but explicable ways. Or maybe we'll find something else, something that doesn't fit, something that forces us to reconsider everything, a spectral signature that's inconsistent with known chemistry, a trajectory change that's too precise to be random outgassing, a signal, faint but structured, emerging from the noise, or nothing conclusive, just more anomalies, more questions, more data that refuses to cooperate with our models. Either way, we'll learn, and learning in the end is the point, not certainty, not comfort. But the endless, humbling, exhilarating process of discovering that the universe is bigger than we imagined, that reality is stranger than we assumed, and that maybe, just maybe, we're not alone. Not in the sense of finding little green men or flying saucers, but in the sense of discovering that intelligence, technology, purpose, these things we thought were unique to us, might be common, might be everywhere, hidden in plain sight, waiting for us to develop the tools and the wisdom to recognize them. Because if 3i Atlas is a probe, if it's watching us, if it's transmitting data back to its creators, then they know about us now. They know we exist. They know we're here, building telescopes, launching satellites, splitting atoms, asking questions. We've been broadcasting our presence for a century, ever since we started using radio. Our signals have been expanding outward at the speed of light, a growing sphere of noise announcing that yes, there's someone here, someone curious, someone technological. And maybe, somewhere across the vast and silent dark, they're asking questions too, wondering if we're smart enough to notice, brave enough to respond, ready enough to meet them. Not physically, perhaps. The distances are too great. Even at the speed of light, messages take years or centuries, but intellectually, philosophically. Are we ready to accept that we might not be the first, that we might not be the smartest, that we might be the newcomers, the latecomers, the children in a cosmos already ancient and crowded? That's the real challenge 3i Atlas presents. Not proving aliens exist, but accepting the possibility, opening ourselves to the idea that maybe the universe isn't dead, that maybe intelligence is common, that maybe when we look up at the stars, someone is looking back. And on March 16th, 2026, when 3i Atlas reaches Jupiter, when it either burns past or slows down or does something we haven't predicted, we'll have our answer, or at least we'll have the next question. Because in science, in exploration, in the search for truth, there are no final answers, only better questions, deeper mysteries, new frontiers, and 3i Atlas, whatever it is asking the best question of all. The question that's haunted humanity since we first looked up at the night sky and wondered. The question that's driven every telescope, every space mission, every search for life beyond Earth. Are we alone? The data suggests maybe not. The math suggests something strange. The trajectory suggests intent. And the timing, the fact that this is all happening now in 2025, when our own technology is finally sophisticated enough to notice, to measure, to ask the right questions, that timing feels almost deliberate, almost like someone wanted us to find it. like someone is testing whether we're ready. Are you paying attention? Are you ready? Are you brave enough to admit that maybe, just maybe, everything you thought you knew is about to change? That the universe you grew up with, the one where Earth is special and humans are unique and life is rare, might be a comfortable fiction? That the real universe, the one three-eye atlas is revealing, might be far stranger and far more alive than we ever dared to imagine? The universe is waiting. It's been waiting for billions of years, waiting for species to evolve, to develop technology, to look up and wonder, waiting for someone to notice the signals, the patterns, the anomalies, waiting for someone to ask the right questions. And so is Three-Eye Atlas, pulsing, breathing, moving, on a trajectory that might be coincidence or might be destiny. 16 hours at a time, getting closer, getting brighter, heading toward Jupiter like it knows exactly where it's going. In less than 2 years, we'll know more. Maybe not everything, but more. And whatever we discover, whether it confirms our hopes or our fears, whether it answers questions or raises new ones, it will change us. Because that's what discovery does. It transforms, it expands, it forces us to grow. So watch the sky, watch the data, watch Three-Eye Atlas. Because history is happening, right now, in real time, and you're here to witness it. The universe is speaking. The question is, are we finally learning to listen?